Welcome back to the part B of lecture 4, and now we are going to start sampling distribution of regression coefficient. However, before we start sampling distribution of regression coefficient, we should little bit discuss about what is sampling distribution. If you already know what is sampling distribution, my recommendation is you can skip this part, and but if you are not so sure, if you are aware of what is sampling distribution, then please continue watching this video. So what we will do, we will try to understand what is the sampling distribution. So sampling distribution is a very interesting concept. Suppose we want to estimate the average body mass index of the students in a large institutions. Okay, now what we will do, we will draw a random sample of size n. So from that large institution, draw a random sample of size n. Okay, so you have probably this kind of data set, like maybe height and weight and ID. Maybe this is first sample, whatever the height, whatever the weight. This is the second sample, drawn from the from the population. This is and the height and weight of the second sample, and then nth sample, height and weight. And using height and weight, we can calculate the body mass index. So suppose this is B1, B2 and Bn. What we are interested in to calculate the average body mass index. So we are interested in average body mass index of the students. So we can simply take B bar, the sample mean of these values. Okay, these body mass indices, 1 by n summation bi I equal to 1 to n. Now B bar is sample average of body mass index. So we want to estimate, the margin of error of B bar, sample mean. Now what we will do, we will sort of do a thought experiment. Okay, we'll do a thought experiment. We'll do a thought experiment. Okay, so what is thought experiment? The thought experiment is, suppose you have infinite resources. Suppose you have infinite resources, lot of resources. Okay, not infinite, I would say lot of resources. We hire maybe 100 many surveyors. Each surveyors maybe 50. Okay, each surveyor go to the same institute and randomly draw n samples. Okay, now randomly draw n samples. What happens is, if previously in real life we will have only one sample, one data set, that's it, and we have to do all the analysis based on this one data set. Now what we will do, we have m many data set. We have m many data set. The first D1, D2, dm, and each data set has computed height, weight and body mass index. Each data set, they have collected height and weight, and from there they calculated the body mass index. Now what you can do, you, instead of one data set, you have m many data set, or if m is 50, they have 50 different data set. So now you can calculate the sample mean from the data set 1, sample mean of the body mass index from data set 2, sample mean from the body mass index from the mth data set. Remember that each of them have n samples. Okay, so now you have this b1 bar, b2 bar, bm bar. Now this vector you can take and draw a histogram of body mass index. So this histogram is the histogram of essentially B bars. So this histogram tells us how the distribution of sample average looks like. So B bar, this distribution tells us how probability distribution of sample average looks like. Okay, so this is an interesting concept. Why? Because you can say that, okay, now since the sampling distribution of B bar looks like this, so we can say that maybe original average B bar, B is somewhere, the body mass index, expected body mass index is somewhere here, and with the some, confidence interval, like you can give a sort of a range that most likely this is where the true value will be there, and if you get a B bar here, then it is likely that it will be far away from the, so you have a sense that whether a sample mean is too far away or reasonably close. So that kind of probabilistic statement now you can make. So sampling distribution enable us to make a probabilistic statement about our estimation. It gives us to calculate what kind of margin of error we can expect. So sampling distribution, sampling distribution helps us to identify, to measure what kind of margin of error you can expect. Now, given this thing, if this is the thing, now this was only for sample mean, but in reality we cannot have many surveyors. This is too much. This is, remember this is a thought experiment. This was not a real life situation. We cannot have many samples. All we have in reality, we have this one sample, that's it. We don't have more than one sample. So we have to calculate this margin of error using the whatever one sample that we have. So turns out that few results, if we assume that B1, B2, Bn, they follow normal distribution with some mean mu and some variance sigma square, then B bar, which is sample mean 1 by n summation Bi, will follow normal distribution with mean mu and variance sigma square by n. So this is the sampling distribution of B bar will follow normal distribution with mean mu and variance sigma square by n. So this is the first result, and this is result 1, and then there is another very interesting result 2, that if we assume B1, B2, Bn, they are independent and identically distributed, some distribution with some PDF, which with some mean expectation of B1 is mu and variance of B1 is sigma square. Okay, then if n goes to infinity, that means if you are for large n, for large n, the large sample size, the B bar will approximately follow normal distribution with mu and sigma square by n. So what does it mean? It means basically your BMI can follow any other distribution. It can follow, say, log normal distribution or some gamma distribution. It doesn't matter. I'm saying it follow any distribution with a proper probability density function, PDF, or probability function. It may follow binomial distribution, all you know. Some proper probability distribution it follows with finite mean and finite variance. Okay, finite mean and finite variance. Then if you ensure you have large enough sample, then the sample mean, the sampling distribution of sample mean will approximately follow normal distribution. And this is a huge result. This is a huge result, and this result is known as central limit theorem. This result is known as central limit theorem. Okay. This is a huge result, and in a sense, if you know that even if you don't have to assume any distribution on the FB, or FB could be any distribution. It could be binomial or Poisson, or it can be gamma, log normal, anything, any distribution, but still all you have to ensure that the sample size is n, and then all you have to do is B is following the sample mean, B bar will approximately follow normal distribution, and this result is known central limit theorem. Now, how can we conceptualize the sampling distribution of regression coefficient? So we have the data like this: height, weight. Then suppose this is the data that we have, 1, 2 up to n. We have h1, w1, h2, w2, ... hn, wn. And we want to say from the height, we want to say something about the weight. Suppose this is the data set that we have. So we want to fit a straight line like this. So we want to fit a WT as a function of say beta naught plus beta 1 height plus some error. Okay. Now what we can think of is we can use this data set using OLS estimator. We can compute the beta hat as beta naught hat, beta 1 hat. Okay, and then what we can do, we can think of, again, do the thought experiment. We can do a thought experiment. Okay, in the thought experiment, what we can do, we can have m many samples. So D1 it's like height and weight. Then D2, another data set, another surveyor go to the field and collect the samples, height and weight, and mth surveyor go to the field and collect the Now what we can do, from each thing we can compute the beta hat, beta 2 hat. So beta hat is beta 1 hat, beta 1 2 hat. Now beta 2 hat is beta 2 1 hat, beta 2 2 hat. From the mth data set, we can compute the mth thing. So beta m1 hat, beta m2 hat. Now what we can do, we can just plot these. Think of this guys as here it is beta 1 hat, here it is beta 2 hat, and we can, if we just plot this guys, so we have essentially a two-dimensional distribution, and this two-dimensional distribution is essentially the joint distribution of sampling distribution of beta hat. Okay, this is the sampling distribution of beta hat. If we just take the beta 1 hat, the intercept for the intercept, so okay, we have used a 0 here, so we can use 0 1 0 1 and 0 1. So here it will be 0 and here it will be 1. So now if we just intercept beta 0 hat, so all we have beta 0 1 hat, beta 0 2 hat, beta 0 m hat. So I, from m data set, I have m intercepts. We can just draw the histogram, and this distribution will be the sampling distribution of intercept. So this is how the distribution will look like. The sampling distribution of beta intercept beta 0 hat, and this will be the sampling distribution of the slope. So that's how we are going to discuss this is the sampling distribution of regression coefficient. Now we will go back and we will start with the regression analytics part B. So now consider our standard linear model. Okay, in the standard linear model, what we have is y equal to x beta plus epsilon, the standard model that we have, and then where epsilon follow normal 0 sigma square I n, and n is greater than p. This is, we always making sure that n is greater than p, because if n is not greater than p, then it is not a OLS estimator is not going to be full rank, so we will not have a proper estimate. So this is required. Now this immediately implies y equal to x beta normal x beta sigma square I n. From here we do also know that least square estimator of beta hat is x transpose x inverse x transpose y. So the question is that ask yourself that what is the sampling distribution of beta hat. So my recommendation is you stop yourself, you pause your video for about 5 minutes, try to figure out what is the sampling distribution of regression coefficient, or the sampling distribution of beta hat in this case, and see if the results match with my what I'm going to tell next. I hope you have found the results by now. So what I'm going to do, I'm going to use this result of multivariate Gaussian distribution or multivariate normal distribution. If you have a vector of size p which follow p-variate normal with mean vector mu and covariance matrix sigma, now you have some coefficient matrix C which is of q cross p dimension, then c times y will give you a new variable z, and this will still follow q dimension normal with mean C mu and variance C sigma C transpose. You can use this result to argue that the sampling distribution of beta hat follow p-variate normal with mean beta itself, the true beta, and the covariance sigma square x transpose x inverse. How can you do that? Now you see beta hat is x transpose x inverse x transpose y, correct? This x transpose x, you can treat it as a C. So you can write beta hat as C times y. Then expectation of beta hat will be, so naturally beta hat will follow, if you write beta hat to be C times y, then you can write beta hat follow some normal distribution. Here in this case it will be p-variate normal with some expectation of beta hat and variance of beta hat. So this will follow normal for sure. You have to only figure out what is the expected value of beta hat. Expected value of beta hat will be expected value of x transpose x inverse x transpose y, which is C. So the C comes out, then it will be x transpose x inverse x transpose expected value of y. Now what is expected value of y? This is x beta. This is x beta. So I have x transpose x inverse x transpose x beta. Now this is x transpose x, this is x transpose x inverse. So this will yield the identity matrix. So we left with beta. Now you have to figure out, you should figure out that how variance of beta hat will be sigma square x transpose x inverse. I'm leaving it for you to figure out. It is very simple. All you have to do, just apply variance this. You have to just apply this result, that variance of Cy is C sigma C transpose. If you apply this, that will be good enough. That will yield you this result, sigma square x transpose x inverse. Alright, next. How we are now taking the sampling distribution of beta naught and beta 1. So we are considering this model MPG as a function of beta naught plus beta 1 times weight plus epsilon. And we have figured out that beta hat follow, in this case beta hat will be essentially beta 1 hat and beta naught hat and beta 1 hat. So this will follow a bivariate normal with beta naught and beta 1 as mean with some sigma square x transpose x inverse. That we have figured out last part of the lecture. So that's how, so since it's a bivariate normal, this is going to be the, so on the x-axis I have put beta naught, on the y-axis I have put the beta 1, and the sampling distribution behaves like this. Okay. Now what I am going to do, I am just taking this same distribution and just including 0 in this picture. So previously you see my x-axis was somewhere between 28 to 45 and minus 9 to minus 2. I'm just expanding the x-axis and y-axis to include 0. So now it is from minus 10 to 2, and it is around including maybe minus 1 to 45. So you can see that this distribution is somewhere here. Now what we can think of, this 95% of the probability mass for beta naught is somewhere in this region, which is far from 0. Here is 0, and 95% of the mass of beta naught actually going to be in this region. Similarly, 95% of the mass of beta 1 is going to be in this region, okay, in minus 8 and minus 6. So that's how we can say that beta naught is far from 0. Similarly, beta 1 is far from 0. It has a negative values, very likely 95% probability, maybe 99% probability that beta 1 is negative, and it has a strong negative correlation. Now what is beta 1? Beta 1 is the slope of weight and miles per gallon. Okay, so that means if I am very confident that weight has a negative correlation with miles per gallon, and because beta 1 is most likely with 95% probability, it is going to take negative value. This kind of probabilistic inference you can do with sampling distribution of regression coefficient. Therefore, sampling distribution of regression coefficient is absolutely foundationally fundamental for doing any statistical inference. So now we have figured out that y equal to x beta plus epsilon, and epsilon follow normal 0 sigma square in. Our OLS estimator is beta hat, which x transpose x inverse x transpose y, and beta hat follow normal. The sampling distribution of beta hat is normal, p-variate normal, with mean as beta itself, that the coefficient itself, with the sigma square and x transpose sigma square times x transpose x inverse. Now residual sum of square RSS y minus x beta hat transpose times y minus x beta hat is the residual sum of square, and it is found that residual sum of square follow scaled chi-square distribution scaled by sigma square, and this is helpful because that means if I have to do any statistical inference on sigma square, then we can use residual sum of square to do that. If we consider residual sum of square as a statistic, a particular statistic, see, it involves only data x, y, x, and beta hat, and we know the distribution is sigma square chi-square with n minus p degrees of freedom. So using this information, we can do a statistical inference for sampling variance or residual variance. Now an interesting thing, that's how to do statistical inference for beta. So for jth predictor, in this case, what we will have, we know that beta j hat, since beta j hat will follow normal beta j, and it will be like sigma square, the ith element of x transpose x inverse, the jth element of x transpose x inverse. If we do that, then essentially we can write beta j hat minus beta j sigma times square root of x transpose x inverse, jth element will follow normal 0, 1. And from chi-square distribution, we know that n minus p s square by sigma square will follow chi-square with n minus p degrees of freedom. So s square, which is residual sum of square by n minus p, what is it implies? It implies expected value of residual sum of square by n minus p is equal to sigma square. So this means S square is an unbiased estimator of sigma square. So S square is an unbiased estimator of sigma square. So this is an interesting result that we have. So note that in the sampling distribution of beta hat, the sigma square is unknown. Since sigma square is unknown, so we have to estimate. One way to do that, we estimate sigma square by the corresponding unbiased estimator of sigma square, S square, which is residual sum of square by n minus p. So if you estimate that with that, then t divided by beta j hat minus beta j. Now if you estimate sigma by s, then this t statistic will follow t distribution with n minus p degrees of freedom. So where s is the standard error of the beta j hat. Now we can test the null hypothesis beta j equal to 0. What we have to do, we have to just put beta j equal to 0 and we will be all set. So how we will do the statistical inference? We will do in this way. So how can we do that? So all we have to do, test the null hypothesis h naught beta j equal to 0. Now what does it mean? If beta j equal to 0, that means predictor xj has no impact on the dependent variable y. That is what it means. Alternate hypothesis is beta j not equal to 0. What does it mean? It means predictor xj has impact on y. Okay. Now under the null hypothesis, the test statistic will be beta j hat minus 0 divided by the standard error of the beta j hat. So what we will do, and that follow tn minus 1, and at 100 into 1 minus alpha % level of significance, if the t observed is greater than tn minus p alpha or t observed is minus tn minus p alpha, then we reject the null hypothesis. So that's how we run the statistical inference for regression coefficient. So another way of doing it is simply instead of looking at the t value, we can look into the p value. The p value is the probability of obtaining the test result at least as extreme as observed result, assuming that the null hypothesis is correct. So we can calculate the p value by multiplying probability of t greater than t observed under the null hypothesis by 2. And then if the p value is too small, then we reject the null hypothesis. Otherwise, we say we fail to reject the null hypothesis. So here is an example, quick example, our example that we have done. So we run my empty curves dataset, beta mpg, beta naught plus beta 1 weight. And so null hypothesis is beta 1 equal to 0 versus beta 1 non-zero. So beta 1 equal to 0 means null hypothesis is saying that weight does not have any effect on miles per gallon. Whereas beta 1 non-zero, the alternative hypothesis is saying that beta 1 non-zero, that means weights do have effect on the miles per gallon. Now the R, if you run the R, typically if you just run lm with mpg $weight with data equal to empty cars, empty cars. You have to put it in some object, say call it summary, and then print summary in sum. If you run these 2 lines in R, then you will get this output. So first is the estimate of the beta naught. This is the estimate of the beta 1. This is the standard error we calculated, and estimate divided by the standard error will give you the t value. So for beta 1, you see the negative 9.559 is pretty small value, and p value is nearly 0. It is rounded off to 0. So we can say that since the p value is really small, we reject null hypothesis. So that means weight has statistically significant effect on miles per gallon, and that makes sense. So if the car is large, it has a lot of weight, naturally its fuel efficiency will be much less. Now we look into another model. So does weight and or horsepower, two predictor model, has statistically significant effect on miles per gallon? So previously we were doing this one. We are trying this model. Yeah, this was my model. We were trying this model. Now we want beta naught plus beta 1 weight, along with we want horsepower as the second independent variable, and we run the same way. We run the R and we get this estimates, this result. So now you can obviously, because your model is different, OLS will give you slightly different estimates. So previously the estimates of beta 1 was negative 5.344. Now it is negative 3.878. So the estimate has changed. Standard error, if you look into the standard error was previously when I have only one independent variable, only weight. That time it was 0.559. Now it is 0.633. So the standard error has gone up. Okay, but still the t value is quite small for both weight and horsepower. P values are also very small, so weight has still have a significant effect on miles per gallon. Okay, it has still have a significant effect, but what we are seeing that standard error of regression coefficient for weight, or the standard error for beta 1, has slightly gone up. So both HP is statistically significant and weight is statistically significant. So what are the interesting thing? Now I am combining both the model. Okay, so the first model is only with weight and miles per gallon, and the second model is weight and horsepower with miles per gallon. So the model 1 is a 2D model and model 2 is a 3D model. Are they comparable? This is the first question we are going to ask. Standard error of beta 1 hat in model 2 is higher than the model 1. So you can see again here the standard error of beta 1 hat in the model 1 was 0.559 and it has gone up 0.633. Why it has so? We will discuss these issues later. These are very important issues, and for now we are stopping here. So we will discuss how to check the model assumptions, because if model assumptions does not hold true, then any inference you do, technically those are not valid. So we will stop here. Now we will do some hands-on. Thank you very much. See you in next video.